Welcome to this explainer. Today, we are diving into a really fascinating, calm theoretical framework that outlines how artificial intelligence learning is fundamentally shifting beyond neural weights. We're going to unpack a document titled A Control Memory Interpretation of Heuristic Learning for Kaggle-Gemma, which details something called the energetic paradigm. Now, right up front, we're not talking about some hyped-up magical breakthrough here. Instead, this offers a deeply structural, analytical way to understand intelligence and how modern AI systems are actually maintained and governed. If you are building or working with these tools today, this is an incredibly useful perspective to have. Here is our roadmap for today. We'll start with the shift to learning beyond neural weights, explain the energetic paradigm, define what control memory actually is, break down signal attenuation, and finally, look at what this all means for the future of AI. Let's get right into it. Okay, let's anchor our discussion right here with this great insight from OpenAI engineer Jia Wang. For the longest time, the standard assumption in the field has been that learning strictly means changing model parameters, right? Just updating the hidden weights inside a neural network. But what we're seeing now is a major shift. The learning object is actually moving away from those opaque parameters and toward explicit, testable artifacts. We're talking about learning through software structures, things like code, tests, logs, and stored memories. So that brings us to section 1, learning beyond neural weights, and this critical shift toward explicit structures. Now, what's really interesting here is how heuristic learning actually validates a major premise of the energetic paradigm, which is the idea that learning happens explicitly outside of neural weights. Think about the old way of doing things with deep reinforcement learning. A system's capabilities lived entirely inside its parameters, which meant a new update could easily overwrite an old capability. We call that catastrophic forgetting, and it's a huge headache. Heuristic learning offers a brilliant way out of that trap by absorbing feedback and stabilizing future actions through external structures. You know, when we talk about external structures, you might immediately think of those old, brittle expert systems from the 1980s. But I want to be clear, this is not a return to that. Traditional expert systems failed because if you added a static if-then rule today, it usually created a hidden, cascading problem tomorrow. The maintenance costs were just exponential. But with heuristic learning, agentic coding sharply drops that cost. Coding agents can continuously test, log, and preserve version histories on their own. The system becomes this dynamic, maintainable structure with built-in regression protection, rather than just a fragile pile of rules. Moving on to section 2, let's look at how the energetic paradigm, or EP, provides a structural interpretation for all of this. EP asks a highly structural question. Out of everything an AI experiences, which constraints should actually be preserved? And which memories should be compressed? You see, EP acts as a control selection layer. It suggests that true intelligence emerges from maintaining these durable control structures, not just from isolated answer generation. It's not just about how an agent maintains its software, it's asking how the agent decides what kind of maintenance is structurally rational in the first place. Which leads us perfectly into section 3, defining control memory. And as we'll see, this goes way beyond basic storage. To really get this, we need to systematically break down how memory is used. First up, we have ordinary memory. This is what you're probably most familiar with when using a standard large language model. It's just temporarily storing the previous text of your conversation. It gives this illusion of having a memory, but once that context window clears or you start a new session, that specific learning is completely gone. If the AI gives a bad answer, ordinary memory just makes a temporary note that, hey, that answer was bad. Second, we have engineering memory. Now, this is a massive step up. In a heuristic system, engineering memory retains actual functional artifacts, tests, logs, version histories, specifically to prevent that catastrophic forgetting we talked about earlier. Instead of just noting an answer was bad, engineering memory might actually add a specific test to the codebase to prevent it from happening again. It actively maintains the baseline capabilities. But here is the really crucial point. EP control memory. This doesn't just store past events or run tests. It actively operationalizes failures into constraints that permanently alter future behavior. It goes beyond checking if a rule was followed. It ensures the fundamental trajectory of the system's reasoning is governed by historical lessons. It is the mechanism that decides what gets remembered, what gets compressed, and what becomes an operational rule. Let's walk through how this builds in practice. This sequence represents the minimal unit of control memory. Let's say a system outputs an answer that looks nicely formatted, but lacks any real causal diagnosis. That is the event. The constraint is the system recognizing that structural formatting without causal reasoning is a failure. The mechanism involves identifying exactly how the system generated that flawed output. And finally, it forms a future action rule, maybe requiring the system to explicitly state its control mechanism before it's allowed to finalize any future output. It's a highly sophisticated progression from raw experience to durable rule. All right, section 4. Let's talk about what happens when an AI appears intelligent on the surface, but structurally it's actually failing. We call this signal attenuation. Signal attenuation is a really critical concept for evaluating AI. Even if you have strong EP reasoning, fundamentally, the final output can still get weakened or attenuated if the underlying model or the prompt layer just can't carry that complex control logic. Essentially, the core logic might be profound, but by the time it gets squeezed through a limited substrate, it comes out looking like superficial imitation rather than deep reasoning. When a system is suffering from this attenuation, you'll see a few specific symptoms. First, structural thinning. This is when the AI keeps the right section titles or formatting, but totally loses the causal engine underneath. Then there's mechanism loss, where it can name constraints but can't actually reproduce the behavior. Memory collapse happens when it starts treating hard operational constraints as just ordinary, temporary conversational context. And finally, compression failure. This is when the system just lazily adds more and more rules and text to a prompt instead of compressing repeated failures into a clean operational mechanism. Finally, section 5. What are the long-term implications here for future AI systems? This table brilliantly illustrates the complementary relationship we've been discussing. Heuristic learning focuses on the software structure, the tests and the logs. It is fundamentally a maintenance paradigm. The energetic paradigm, though, targets the control structure. It's the governing force. Think of it like this. A coding agent can patch and test a system all day, but it needs the energetic paradigm to decide what kind of patch is structurally correct, keeping the system from just gaming its own tests or accumulating hidden technical debt. Ultimately, this theoretical framework is telling us that AI has to evolve. We've spent the last few years optimizing these models to be absolutely incredible at generating isolated answers. But true, long-term capability requires moving away from just producing answers and moving toward maintaining stable intelligence through controlled structures. We need systems that don't just guess the next token accurately, but that actively preserve constraints, compress their history, and turn their failures into durable, lasting architecture. So, as we build systems that rely less on hidden neural weights and much more on these explicit, manageable software structures, we're left with a massive question for the field. If future AI systems learn through external structures, what principles determine which experiences become durable knowledge? Thank you so much for joining me on this explainer. I hope this look into the energetic paradigm gives you a solid analytical framework for thinking about the road ahead for artificial intelligence.